Hey guys, this is the fifth of our 9 common techniques for rewriting integrands. In this video we're going to learn how to add a well-chosen zero, or learn when we would add a well-chosen zero. Of course, if your basic rules apply or U substitution applies, you don't want to do any of this stuff. You always want to go with the easiest rule first, basic rules first, then U sub, and if nothing else works, try one of these. Here's an example where you might add a well-chosen zero. I'm going to do the simplest example first. Now you might think long division would be appropriate in this case, and you'd be right. Long division is appropriate. I've got a polynomial divided by a polynomial, and the degree of the polynomial in the numerator is equal to the degree of the polynomial in the denominator. So that's one case where you would use long division. This is also a case when using a well-chosen zero will make things easier. So we'll just say use this technique when the integrand is a rational function and the degree of the numerator is equal to the degree of the denominator. You could also use long division, but this is faster in this case. There's another case when we would use a well-chosen zero as well, and I'll show you an example of that. So here's the idea. We look at this and say, wouldn't it be nice if that was just an x squared plus 100? Because if it were an x squared plus 100, all I would do is divide x squared plus 100 by x squared plus 100 and I'd get a 1, and that would be really nice. But unfortunately I don't have that. I've got a 3x squared and there's no 100 there. And say, well, what can we do? Well, in that case we can add a well-chosen zero. We're going to add exactly what we want so that everything cancels nicely. And that's okay as long as we compensate for adding that by subtracting it. So we are literally adding 0 to our expression, adding 0 to our integrand, but we're doing that so that we can write it in this different way. And once it's written in that different way, it'll be easy to take the antiderivative. Notice, first of all, that I do not have an anti-differentiation rule for this. It's a polynomial over a polynomial. U sub, derivative of the denominator, is 2x. There's too many x's in the numerator. So U sub doesn't work, basic rules don't work. So we're going to try well-chosen zero. The first thing you want to do with the well-chosen zero technique is factor out any constants. So I've got a 3 in front of the x squared, so I'm going to factor that out. And I'm leaving a bunch of space so that I can add and subtract exactly what I want to add and subtract. Now the idea is, I would really like to have an x squared plus 100 here, so it would cancel with this. So I'm just going to make it what I want it to be. It's x squared plus 100. That's totally fine, totally legal, as long as I also subtract 100. And now all I've done is add 0 to the whole thing. And that's nice, because once I've done this, I can just do this divided by this, plus this divided by this. It's just separating the numerator like we did a few examples back, a few techniques back. We're going to get exactly the same result we would have gotten had we done long division. So I'm going to separate the numerator now. X squared plus 100 over x squared plus 100 minus 100 over x squared plus 100. And that is a 1. It's not a 0. Some students cancel those and make that a 0. It's just a 1. Minus 100 over x squared plus 100. And that's an arctan. So let's do this. I think I would like to distribute the 3 back in. 3 times that 100 is 300. I'm going to factor that 100 times 3 out. So now that looks like a basic rule, and that looks like a basic rule. The antiderivative of a constant is a constant times your variable, which is just x. Then I bring my 300 down. That's my constant. Here, a squared, that's the constant in the denominator, that's 100. So a equals the square root of that, so that's 10. And now I'm just using my basic rule for arctangent. If you have 1 over a squared plus x squared, where a is the constant, you get 1 over a times arctan of x over a plus c. And a is 10. So we're going to have 1 over 10 times arctan of x over 10 plus c. And then we simplify. 300 divided by 10 is just going to give me 30. So we get this. Ta-da! Alright, that's the well-chosen zero technique. But the key is, with the well-chosen zero technique, you see the degree of the numerator and denominator are the same. And we're avoiding long division. Like, we could do the long division, but we don't want to. We'd like to do this simpler thing. So we factor out the constant, and then we add and subtract exactly what we want, so that this would cancel with this, and so that that over that is a rule that we have. And that works. That works in all the functions that look like this. Now, if there happened to be like a +2 or something like that up here, you could do the same thing. You would just separate the numerator first. So you'd have another term as well that you'd have to take care of. So that's one example where you'd add a well-chosen zero. Now here's another one. Now this is one that can be solved a number of ways. I'm going to give you another technique for this as well. But notice, initially, it looks like a u sub. I really, really want to do a u sub. Now, a lot of students also would like to bring this e to the negative 4x up to the numerator and make it e to the positive 4x. We cannot do that because of this plus sign. That's not legal. We cannot separate the denominator. We can separate the numerator, like we did here. We can do that divided by that plus that divided by that. Totally fine if it's terms in the numerator. It's not okay in the denominator. If I have a over b plus c, that's not the same as a over b plus a over c. Like, if c and b are two different numbers, those are different size pieces of pie. Like, you can't do it. It's just not legal. You should try plugging in values of a, b, and c and showing that that does not work in general. So you cannot separate these two guys. So then my gut instinct is, okay, well, if I can't do that, I could do a u sub. A lot of students think u might be e to the negative 4x. And that'd be okay. Du would be negative 4 dx. But I'd still have a 3 plus e to the u in the denominator. So that's looking pretty bad. So my next choice, my initial choice, would be, let's let u be the denominator. And then let's take the derivative of u and see if it's up there somewhere. Is du a factor? And we can always adjust constants as necessary. The derivative of 3 is 0. The derivative of e to some power is e to that power, so you're just going to copy the exponential down. Looks exactly the same as before. And then you multiply by the derivative of the inside. Derivative of a constant times x is just a constant. Don't forget your dx. Do I have an e to the negative 4x dx up here somewhere? I don't. I've got an e to the negative 4x in the denominator, but I don't have one that matches in the numerator. So it's a bit of a problem. So the u sub is going to fail us. So you might say, okay, well, can't I do the same thing here that I did here? Well, maybe. Maybe if I multiply by just, or if I add and subtract just the right thing, what I have in the numerator would cancel with what I have in the denominator. So I'm going to try that. So I have 2 up here over 3 plus e to the negative 4x. In order for everything to cancel and everything to be nice, I need a 3 plus e to the negative 4x up here. If I add 1, that's going to give me a 3. If I also add e to the negative 4x, that will work. And now I've got a 3 plus e to the negative 4x up here to cancel with that down here. But I have to compensate for everything I added up there. I also have to subtract it. So I'm going to subtract 1, because I added 1. And then I will subtract e to the negative 4x, because I added that. And now I'm going to rewrite it differently. I've got 3 plus e to the negative 4x minus 1 minus e to the negative 4x. I'm grouping these two guys together and these two guys together. Of course, we're adding those. Those are in our numerator. And all of those are divided by 3 plus e to the negative 4x. So now I can separate the numerator. This over this, that's 1. And then this over this, hey, that's looking pretty good. Looking very good now. Okay, let's keep going. This over itself is 1, which is what we wanted. Oops. That should be plus a minus. Or we could subtract the quantity 1 plus e to the negative 4x over this. Well, u sub work for this one now. If u is that denominator, I need the matching exponential in the numerator. I've got that for this, but this minus 1 is a little bit of a problem. So I guess we could split that up. I think I'm going to distribute that negative again. Sorry, guys. So that'll be a u sub. And this one, we might have to do the well-chosen 0 thing again. Gosh. It's getting cyclical. I feel like I have to keep doing this over and over and over again. Do I ever get rid of them? We'll see. But I've got a rule for that, and I've got a u sub for that, and then the question is, what can I do for that? If I try the well-chosen 0 thing here again, I'd need to add 2 and add e to the negative 4x in the parentheses, and that's okay as long as I also subtract 2 and subtract the e to the negative 4x. Whew, it's a lot of work. And then these two guys, that's that over that. And if I distribute that negative, I guess it's not going to work. I guess we've got to use the other technique on our list for this one. It's just getting worse and worse. You might say, how do you know? Well, that's a 1. That's a minus e to the negative 4x over our denominator. That's a minus 1. The 1 and the minus 1 are gone. And then I've got plus 2 plus e to the negative 4x over this. Do you guys see what I did? The numerators are, the denominators are the same, so we can keep the common denominator, add the numerators. I've got a negative one of those exponentials plus a positive one of those exponentials. Everything's canceling, isn't that beautiful? But wait a minute. What do we have here? Exactly what we started with. So I guess that is not a good technique, well chosen 0 for that one. I see the problem though. Everything would have worked out just fine if that was a 3 and that was a 3. Because then I would have just added and subtracted an exponential, and I could have done a u sub for that exponential part, and then just had a 1 over here. It's because the constants are different that this technique doesn't work. So I think I'm just going to hold off on this problem. We're going to do this problem again when we look at, I think it's the 9th technique on the list. Or no, the 8th technique on the list, multiplying and dividing by an exponential function. Yeah. In that section, we will be able to write this in such a way that we can immediately do a u sub, just like the u sub that we wanted to do here. Now we could use the well-chosen 0 technique if those constants were the same. So we're going to come back to this problem. When we study technique number 8, multiplying and dividing by an exponential. There we go, sorry. But I will say the well-chosen 0 would have worked if that constant 2 was equal to that constant. If that was a 2 and that was a 2, it would work. If that was a 3 and that was a 3, it would work. This doesn't work because those numbers are different and that negative 1 pops up. And that's a problem for our u sub part. I really wanted to be able to do a u sub here, and I can't because of the negative 1. Okay, so let me show you how we would solve this very similar problem where that 2 is replaced by a 3. Just leaving this for your notes. Try technique number 8 instead for this problem. Okay, so here's a problem where a well-chosen 0, or adding a well-chosen 0 does work. So let's say we've got 3 over 3 plus e to the negative 4x dx. The u sub that we talked about before doesn't work. But if I add e to the negative 4x and I subtract e to the negative 4x and group like this, it's going to work. We'll have this divided by itself. Minus that exponential divided by this, and check it out, that's just a 1, and this is a great candidate for u sub, and we know it's a great candidate for u sub because the exponential down here, when I take its derivative, I get the same exponential up here multiplied by a constant. I need matching exponentials for the u sub to work. When I had a constant up here, I couldn't do u sub until I manipulated it in this way, and now I can do u sub. So let's just take the antiderivative of 1, which is x, and then I will do this part separately. Alright, so let's do a u sub. We're going to let u be the denominator. Du is the derivative of u times dx. Remember, derivative of 3 is 0. Derivative of this exponential is exactly the same exponential times the derivative of the inside by the chain rule. Don't forget to multiply by dx. Now, I don't have a negative 4 up here. I just have 1 e to the negative 4x. So I'm going to divide both sides by negative 4, which is the same as multiplying by negative 1/4. So this guy is a negative 1/4 du. And this guy is a u. So we end up with this. I've got x minus a negative 1/4 du. So I'm going to make that a negative, and a negative is a positive 1/4 du, factor it off to the right. I've got a u in the denominator, still an implied 1 in the numerator. So that gives me x plus 1/4. Antiderivative of 1 over u is natural log of the absolute value of u plus c. Oops, excuse me. U is 3 plus e to the negative 4x. You can stop there. That's a perfectly good answer for a test or a quiz. But if you're checking your answer in the back of the book, you're not going to see these absolute value bars because this exponential is always positive. E to the negative 4x looks like this. And when you shift it up 3 units, it's just the same thing. Shift it up 3 units like that. It's going to have that shape. But look at the y values on that graph. Those y values are definitely positive. These y values are definitely greater than 0. These y values are definitely greater than 3, as they're getting very, very close to y equals 3. But they're never 0, so we don't need absolute value bars. So this would be a fine answer. But if you're checking your answer in the back of the book, they're not going to have absolute value bars there because they know that that function's positive. All right. So let's go back. Well chosen 0. When do we use it? This is when I tend to use this technique. If I've got a rational function as my integrand and the degree of the numerator and degree of the denominator are the same, it just is a shortcut for doing the long division. You can do the long division, you're going to get exactly the same answer. But we just add and subtract just the right thing so that this cancels with this, and hopefully you have a basic rule for the other part. Now, this problem looked like it might be a good candidate for adding the well-chosen 0, but it wasn't. Because in order to make that 2 a 3, I had to add a 1. And adding that one meant subtracting that one, and subtracting that one meant the u sub didn't work over here. So this is not a good candidate for the well-chosen 0 because that 2 and that 3 are different. But this one is. This is a great candidate because that number and that number are exactly the same. I can add and subtract exponentials as I want. And then when I do, I get just something that reduces to a constant and then something that reduces to a u sub. And let me show you one more example. Students often see this example and they get a little tripped up. They get tripped up here because we've talked about this. Let's say you see this. Are you going to do the well-chosen 0 or not? No, you absolutely do not want to do the well-chosen 0. You might say, why? Well, there's no 5 out here, first of all. You say, well, I can multiply and divide by 5. That's true. There's no negative 4 here. Well, I can subtract 4 and then add 4 to compensate. That's true. But the reason I don't want to use that technique here is because basic rules don't apply, but U substitution already applies. There is an exponential in the denominator that already matches the exponential in the numerator. So I can just do U sub from here, and I'll be good to go. Now this one, remember what it looked like before I modified it. It looked like this. Here it is in our memory. It looked like that. Those numbers were the same, but there was not an exponential in the numerator to match that exponential in the denominator. So I needed to modify it somehow, and adding the well-chosen 0 did it for me so that I could use U sub. This one's already got U sub, or it's already ready for U sub. So on this one, I'd go straight to U substitution. I would not use my well-chosen 0 technique. I'd let U be the entire denominator. Compute du, 5 times the derivative of e to the x over 2. It's the same exponential. Derivative of the inside is 1/2. Don't forget the derivative of the inside by the chain rule, times dx. I want to get this exponential by itself because I have an e to the x over 2 dx as a factor. It doesn't have a 5/2 out front. So I'm going to multiply both sides by 2 over 5. Gets rid of that and that. All right. And remember, this was our u. So we end up with a u in the denominator. And this part turns out to be 2/5 of du. I'm going to pull my 2/5 out to the left, my du off to the right. There's an implied one in the numerator, and look, it's another natural log. These are almost always natural logs. I'm leaving space for my u, and then remember u was 5 times e to the x over 2 minus 4. So plug that back in, and that's your answer. So this is a u sub, not a well-chosen 0. This is a well-chosen 0. And this guy, we've got another technique for. We're going to use technique number 8, multiplying and dividing by an exponential. But this is a great candidate for well-chosen 0. When the degree of the numerator and degree of the denominator are the same. Just factor out any constants and add and subtract what you need in order to apply your basic rules. You can also do long division, but this allows you to avoid long division.